right, thanks for watching. And today I would like to give you a beautiful taste of the world of convexity, which in my opinion is the most important concept in all of applied math. And in fact, at the end, I will give you a beautiful application to PDEs. So suppose you have a function f, let's say from R to R, then what does it mean for f to be convex? So f is convex if, and it turns out there are three different definitions of convexity, depending on how many derivatives you have. But first of all, some typical examples are x squared or e to the x. And convex, if you have two derivatives, it just means concave up. So if f double prime of x is greater or equal to 0 for all x. So that's the definition in calculus if you have two derivatives. It turns out there's a slightly more general definition if you only have one derivative, and this is by considering tangent lines instead of functions. So convex would simply mean that f is above any of its tangent lines. So if this is x and this is another point y, then f is above the tangent line of x. So in other words, we can just simply write that as f of y is greater or equal to the tangent line at x, which is simply f of x plus f prime of x times y minus x. And this, in my opinion, is the most important definition, at least in PDEs. And the reason is as following. In PDEs, you usually need inequalities. That's what makes it work. And generally, it's very easy to find inequalities for less than or equal. But it's very hard to find inequalities with greater than or equal. But it turns out exactly this one gives us greater than or equal. And in fact, there's, this is why PDE people, they care about convexity. Last but not least, there's even a definition with no derivative. Simply, if you replace the tangent line with secant lines. So here, f is convex if and only if it is below any of its secant line. Now, how do you write secant line? Well, if this is x and this is y, then any point of the segment x comma y can be written as 1 minus tx plus ty. And what we're saying is that f at that point, so f at 1 minus tx plus ty is less than or equal to this combination, but with f of x and f of y. So it's less than or equal to 1 minus t f of x plus t f of y. It's almost like linearity, except you put, less than or equal. And also t is between 0 and 1. And just FYI, why are those three things equivalent? So for 1 and 2, you just use Taylor series. So by Taylor's theorem, those are equivalent. And for this one, essentially, you just write a tangent line as a limit of secant lines. And so you can go from 2 to 3 as well. Now, as I mentioned, it is the most important concept in applied math, and especially with optimal control. Because in optimal control, you're trying to find minimizers, and it turns out convexity is what gives you minimizers. And it also appears naturally in the calculus of variations, simply because of the following fact. It seems obvious, but very important. If f is convex, so suppose maybe strictly convex, then critical points of f are equivalent to minimizers. So in other words, if you already know your functional is convex, then in order to find a minimum, you just need to find a critical point, and then you're done. That's why we really like convexity. It helps us find minimizers much easily. And as promised, here is a nice application to PDEs. And you'll see this is quite unbelievable because really convexity appears in a miraculous way. So PDEs in particular, let's consider the heat equation, UT equals UXX, or sometimes called the diffusion equation. And what does it do? Well, if you have a metal rod from 0 to L and you consider an arbitrary point X, then U of xt gives you the temperature of this rod at time t and position x. So something very powerful. And what we would like to ask ourselves is, well, there is uniqueness of solutions, but is there backwards uniqueness? Uniqueness. And by backwards uniqueness, I don't mean sesneu qui nu, not uniqueness written backwards. I really mean the following scenario. So suppose you have two functions u and v that satisfy the heat equation. So ut equals uxx and vt equals vxx. And suppose for some terminal time they are equal. So maybe in terms of a picture, if this is x and this is a rod from 0 to L and this is time t, and suppose for some terminal time t, we know that u equals v. The question is, does it follow that u equals v everywhere? So do we have u equals v? And in general, the answer is no, because heat is irreversible. If you see a source of heat, generally you know nothing about its past. And this, for instance, is useful for Brownian motion, because if you do Brownian motion like that, pretty smooth, then if you're at some terminal point, you generally do not have any idea where you came from. And in fact, as a little application, well, if you take the backwards heat equation, this minus, then this is unsolvable. So this is ill-posed. You can't do this. That said, here's a cool thing. If we know what u and v are at the terminal time, and you also know that u and v are equal on the boundary, then it turns out the answer is yes. Okay? So if u and v are equal at the terminal time and at the endpoints, then u and v have to be equal everywhere, in particular originally as well. So if you, let's say, at year 3000, you see some some fire match that an alien lit, okay, and you know kind of what happens at the boundaries, then you can figure out exactly how hot it was when the alien lit that match. Some people say it's pretty lit, and I agree. So what do we want to show here? So theorem. So simply by considering the difference, what I say now is equivalent to what I said, namely, if u solves the heat equation and u is 0 at the terminal, uxt is 0, and basically u 0t equals u lt for all t, so equals 0 for all t. So again, suppose u is 0 here and 0 on the sides, then it turns out u is 0 everywhere. U of xt is identically equal 0. And as I said, it's equivalent to what I said just by considering the difference. So we're kind of saying if the null space is 0, then we have uniqueness, which is very typical. And as I said, the beauty is not in the result. The beauty is in the proof, because that uses convexity in a very hidden way. And in order to do that, we would like to define some energy functional. So let E of t just be the usual energy, 1/2 integral from 0 to L of u of xt squared dx. So for some fixed time t, we would like to integrate the square of u on the rod. And then as usual, consider the derivative. So e prime of t, it's 1/2 integral from 0 to L of chain loop. So 2u ut, this 2 cancels out. And here's the important thing. If in a PDE problem, you do not use the PDE, you're in trouble because you can't have all those amazing results for all the functions in the world. So here, definitely use the fact that ut equals uxx. And the beautiful thing is this is an invitation to integrate by parts. So put the x here. And what we get is minus integral from 0 to L ux times ux. And the nice thing is there are no boundary points because u equals 0 on the boundary. Okay. And so in particular, what we get, e prime of t equals minus integral from 0 to L of ux squared. So yes, the energy is decreasing. And generally you use that to show that u is 0, except the only issue is we don't know what happens at u at the initial point. We don't know what happens at 0, so we cannot just use the same proof. Instead, let's continue. Let's find e double prime of t. And by the way, what we want to find, we would like to find what's called a differential inequality. Inequality for E. So like a differential equation, but with less than or equal in some sense. Kind of think Grunwald's inequality. So then, well, if you continue, if you do E double prime of t, that becomes minus, again, minus integral from 0 to L, chain loop, so 2 ux uxt dx. And then what you would like to do is, again, integrate this by parts. So this becomes plus, so minus minus, so plus integral from 0 to L, uxx, and then ut dx. But again, by the PDE, this just becomes uxx. So that becomes 2 integral from 0 to L, uxx, that is 2 times integral from 0 to L, uxx squared dx. So it's not dos x, it's cuatros x. Stay convex, my friends. And in fact, it turns out that here, E double prime, yeah, this is positive. It is true that E is convex, but this is completely useless. So it turns out the fact that E is convex doesn't help us at all. And instead, what we would like to do is the following ingenious trick. And that's what I love about PDEs. There are a lot of really clever insights. Because let's go back at our 3 things that we learned. We had E, it's 1/2 integral of u squared. And then we had E prime, which is minus integral from 0 to L u of x squared. And finally, E of double prime. And that becomes 2 times integral from 0 to L uxx squared. And what we would like to do is balance this middle term with the first term and the last term. So it turns out this is kind of sort of squeezed between E and E double prime. And in order to do this, consider the square of E prime. So it's minus integral from 0 to L u of x squared. Okay, and the minus squared is just plus, so integral from 0 to L ux squared. And ux squared, you can just write this as ux times ux. And again, another integration by parts. So this becomes minus times the integral from 0 to L of uxx times u squared, but again, minus squared becomes plus. So this is e double prime squared. But here's a nice thing. Well, this uxx comes into this e double prime, and u is an e. So it would be nice if we could separate out uxx and u, and it turns out there's a perfect inequality for this, which is the Cauchy-Schwarz inequality. So integral of fg squared is less than or equal to integral of f squared times integral of g squared. So this becomes integral from 0 to L of uxx squared times integral from 0 to L of u squared. And this is almost e times e double prime. The only thing is we need to multiply this by 1/2 and divide this by 1/2, so multiply by 2. 0 to L of uxx squared. And indeed, and so in the end, what do we get? E prime t squared is less than or equal to e of t times e double prime of t. And this is your differential inequality. So again, your inequality, but with derivatives. And we'll see very soon why this is useful. And again, I promise you the convexity will come at some point, but we just need to do a little bit of analysis, because remember, what was e of t? Okay, that's integral from 0 to L, u of xt squared dx. And ideally, what we would like to show, we would like to show that this is identically equal 0, because then u would be 0, and then we would be done. Okay, so that is our goal. And in particular, one thing though to notice, we still have not used the terminal condition. But now notice e at the terminal time is integral from 0 to L of u of x capital T squared dx. But this is 0, and therefore at the terminal time, e is 0. So if this is capital T, e is 0 there. And now let's do our contradiction. So suppose e is not identical equal 0. Then of course it means it has to be positive at some point, but let's use this condition a little bit. So if this is at capital T, we know e is 0 here. Possibly it could be 0 for a longer time, but because it's not identically equal 0, there has to be a time where it switches from 0 to positive. And in particular, let's call this T star. So in terms of analysis, let T star be the infimum of values of T between 0 and capital T, such that E is identically equal 0 on the interval T comma capital T. And because E is continuous and it's not identically equal 0, we know that this is positive. So there's got to be a positive time where E switches from positive to 0. And what we would like to do, we would like to find a contradiction. Namely, we would like to find some small epsilon such that E is 0 on that small interval as well. So go show E is identically equal 0 on T star minus epsilon comma T star on for some epsilon. Because that would contradict the smallness of T star, because T star minus epsilon would be smaller. All right. And now, as promised, here is where the convexity comes in. So step 5. Because now what we would like to consider is the following function. So not e of t, but ln of e of t. So consider this one, and I promise this will be convex. And for this, let's calculate the derivatives. So f prime of t by the Chen-Lu, that is e prime of t over e of t, and then the second derivative, f double prime of t, that is e double prime of t times e of t minus e prime of t squared. So e prime times e prime, again, by the quotient law. Almost wanted to say quotient law, but that's different. All right, so we have this monster. And we just want to ask ourselves, man, if only there was a inequality that could tell us something about that. But wait a moment, let's scroll up a little bit. We found it. E prime squared is less than or equal to e times e double prime. So by the inequality above, we actually get that f double prime is non-negative. So in fact, f is convex. All right, so now we got that f is convex by the first definition of convexity. And now what we would like to use is the secant definition of convexity, namely that f is below any of its secant line. So this is, let's say, x, and this is y. Okay, so again, f of, this 1 minus tx plus ty is less than or equal to 1 minus tf of x plus tf of y. But now the question is, what are x and y? And for this, note the following. So again, we know this is e, it's 0 here up to t star. But now, by continuity and the definition, we know there's a small interval where e is positive. Because you see, this is the last time this is 0. And before that, e has to be positive, at least for some short time. So we know there is epsilon positive, such that, again, all of this is by continuity, such that e of t star minus epsilon is positive. In fact, that's all we need. We don't even need positive on the whole interval. We need positive at some point. All right, and then what we would like to use, we would like to use this for y and this for x. Okay? So now, as I said, let's use the fact that f is convex. So since f is convex, f of 1 minus tx plus ty is less than or equal to 1 minus t f of x plus t f of y. And again, that's for all t between 0 and 1. But now, so f was ln. So essentially, we get ln of e of 1 minus tx plus ty is less than or equal to 1 minus t ln of e of x plus t ln of e of y. All right, and to get rid of this ln, we just exponentiate. So do e, whee, and we get e of 1 minus tx plus ty. So again, by rules of exponents, this becomes less than or equal to e of x to the 1 minus t, and then e of y to the t. But now remember, what do we know? Well, y is t star. And by definition, we know e at t star is 0. So in particular, e of y is actually 0. And so basically this energy, which I like to remind you was positive, is actually less than or equal to 0. So e of 1 minus tx plus ty is identically equal to 0. And so basically, between x and y, we know that in that segment, e is identically equal to 0. So in terms of our picture, if this is t star and this is t star minus epsilon, then e, we just showed it 0 here and that's 0 here. And again, that is a contradiction. So e is identically equal 0 on the interval T star minus epsilon and T star. And again, it contradicts the smallness of T star. And therefore, we have our backwards uniqueness. And again, big box at the end. Actually, it took me, I'm not kidding, 2.5 hours to record this, but it's just for you, my subscribers. But again, I really think this is such an ingenious idea of convexity, because there's this energy method trick with Cauchy-Schwarz, and then you use the equivalence of the second derivative definition and the secant line definition, which is quite neat. All right, I hope you like this little convexity extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.